So let's talk a little bit about amplifier noise in our receivers. The Johnson-Nyquist noise, in other words, thermal noise, was defined as early as 1920s as filtered thermal noise, which has a filtered wide power spectral density that looks as in a figure. Okay. Now, as you know, noise PST and not was characterized as KT, temperature in Kelvin times Boltzmann constant. So, and the total noise that is emitted depends on the bandwidth B, right? Now, with 1 hertz bandwidth, Pn is at noise at room temperature at 290 Kelvin is around negative 174 dBm. Okay, the noise floor. Of course, the actual noise floor in receivers depends on the receiver electronics, how old the components are, the temperature, etc. All devices generate internal noise, in addition to the noise that comes in to them at their inputs. It is important to characterize this additional source of noise in order to make correct predictions of our communication system performance. Okay, so here is the model. Some signal comes in, noise is added to it before it comes into the amplifier already. So the signal plus noise comes to an amplifier stage at our receiver front end, for example. And this amplifier has a power gain G, suppose, and it also adds its own internal noise. The model is the signal is multiplied by the gain of the amplifier. The incoming noise and I is again multiplied by the gain of the amplifier, and there's a new noise term added. Okay, so in order to characterize the reduction in SNR as the signal passes through the amplifier, a parameter called noise factor is defined. Noise factor is defined as the ratio of the input SNR to the output SNR. The input SNR is the SNR at the input of the amplifier, the ratio of PSI, the power of the signal term, to the power of the noise term. And output SNR is the ratio of the output signal power to the output total noise power. The total output noise power from this model is given by gain times the amplifier gain times the input noise power plus the additional noise power. Okay, so we have G times P and I plus P and X divided by G times P and I. Okay, it's just simple calculation. Now we define something called a noise figure. You know, we like adding dBs to dBms, right? So we define a dB noise figure, which is simply 10 log to the base 10 of the noise factor. Okay. Okay. Since the noise factor is always 1, because SNR can only increase, there is no system that can clean up the noise and increase the SNR, right? So the noise factor always is larger than 1. So the noise figure is always a positive quantity. Okay. But there's a strange definition of the noise figure and the noise factor as well when there are multiple amplifier stages cascaded together. So basically, here's the strange definition. The noise factor is measured with respect to the receiver input. Okay, so basically, even if there are multiple stages, cascaded stages, the noise factor of the second stage is computed not with respect to the output of the output noise of the first stage, but it is computed with respect to the overall system input. I'll make it clearer in a few minutes. So let's see. First of all, let's worry about only one stage. Suppose I have this amplifier with input noise minus 174 dBm per hertz. The gain of the amplifier is 10 dB. The gain of the amplifier is 10 dB. The noise factor is 3 dB. What does this mean? For the output noise, okay, we have minus 174 dBm per hertz plus 10 dB gain plus 3 dB noise factor, which is going to give us minus 161 dBm per hertz. Now you may ask why, so let's do some computations. First of all, let me open up a notepad, okay, and let's worry about what is going on here. So now, with one stage, okay, this is G, this is PS in, P noise in, okay, and there is a noise added, right? So F is SNR in divided by SNR out, which is, as we computed in the slide, G, P, N, I plus Nx divided by G, P, and I. Okay. So if you think about the dBm noise at the output, so SNR out is SNR in times F. So SNR out in dB is SNR out in dB, right? Plus the noise factor. Noise factor is the dB version of noise figure, right? But this is basically P.
There's a mistake.
Yes, please. Oh, thank you.
Shouldn't F be at the SNR outside?
Oh, yes. Thank you. So this should be And this should be negative, right? How about that? Okay. So now, let's so now let's do some computations on a two-stage. So consider a cascaded system of amplifiers. Suppose because we have two stages. Okay, noise comes in, there's a gain, and there's added noise. Okay, and there's a second stage. Okay, and there's an output noise. Okay, so F is going to be the output noise divided by G1, G2 times the input noise. Okay, now the output noise is going to be N2 plus G2 N1 plus G1 G2 and N. All right. So F is 1 plus G2 N1 plus N2 over G1 G2 and N, which is 1 plus N1 over G1 and N plus N2 over G1 G2 and N. Okay, in other words, well, this is G1 and N plus N1 over G1 and N, right? And this is 1 over G1 F2 minus 1. Hence, the equivalent noise factor is F1 plus F2 minus 1 over G1. So when we cascade two amplifiers together, the equivalent noise factor is given by the sum of the first noise factor plus the second noise factor minus 1 over the gain of the first system. This is how it turns out to be when we applied the definition of the noise factor to a cascade system. So by induction, you can extend this to n stages as F equals F1 plus F2 minus 1 over G1 plus F3 minus 1 over G1 G2 plus Fn minus 1 over G and Gn minus 1 up to G1. Okay, so what is the consequence of this? Notice that amplifiers that come later in later stages are less important in terms of the added noise, because the noise contribution, the contribution of the noise to the noise figure is reduced by the gains of the previous stages. Okay, so amplifiers that have high noise factors are better placed toward later stages. We want front-end amplifiers to be better quality, to be lower noise. Okay, because they contribute most to the overall noise factor of the system. Okay. So that's why often we use a low noise amplifier at the front end of the system. So let's see now. Let's go back to our slides. Okay. Now, based on this formula, as I said, we use low noise amplifiers as the first stage in receivers. For example, when you have these two cascades, consider two amplifiers with gain 10 dB each, but one has noise figure 3 dB, the other has noise figure 6 dB. Okay, the total gain, whether you place one first or the other, is going to be 20 dB. That's not going to change. But when you cascade, when you put the first one first, the total noise figure is going to be 3.62. When you place this one first, the total noise figure is going to be 6.3. Again, how do we compute this? We use noise factors. Let me see if I have that computation here. So let me try that. Okay. So let's compute F here. F is going to be the first noise factor, which is what? What is 3 dB? 2, right? Okay, plus the second noise factor minus 1 over G1. What is the second noise factor? 6 dB. 6 dB corresponds to 4. 4 minus 1 over 10, which is, did I do this right? Oh, wait. Yeah. I'm doing this right. Okay, so 2.3, which corresponds to a noise factor of 3.62. Okay, let's do the other computation. If the higher noise factor amplifier was placed as the first stage in the cascade, it's called F prime. That is 6 dB. 6 dB corresponds to a factor of 4. 4 plus, well, 3 dB corresponds to a factor of 2. 2 minus 1 over 10, which is 4.1. That corresponds to a noise figure, effective noise figure for the first two stages of 6.3 dB. Okay. So it is advantageous to put lower noise amplifiers to the front of the cascade. Now, so here is an example of several components. There's a wide bandpass filter, a low noise amplifier, an image rejection filter, and an IF amplifier after the local oscillator. Okay, so the gains and the noise factors of all of these components are given, and you are asked to compute the eventually effective noise figure of this system. And then we will use this as part of the link budget. Okay. So how do we do this? Okay, let's compute. Let's compute noise factors. Okay. So let's compute. Let's switch the let's convert the noise factors to noise figures, or the other way around. 1.12 to 1.25 for 3.16. Okay, so I would like you to think about this cascade. Okay, so do this as homework. Compute what is going to happen to the SNR at the output of this system. Compute the effective noise figure of the cascade and see for yourself what's going to happen to the SNR at the output of the system. Okay, and